Hello everyone. In this video, we're gonna go over getting information from the graph of a function. So let's start with a basic example. So in this example, you see the graph of the temperature function is given. It's asking us to first find the temperature at 1 p.m., 3 p.m., and 5 p.m. It's between noon and 6 p.m. So T1, T3, T5. So you go to 1. For functional values, you just look at the height. So we can simply just look at the height. That height is, you see in this case, it's 25. So T of 1 will be 25. And then if you go to T of 3, T of 3 will be, you look at the height at 3, it's going to be right here, which is going to be 30. And then if you look at T of 5, that's going to be 20. So these are the temperatures. So in the next one, it says which one is larger, T of 2 or T of 4. You can look at T of 2 is right here. T of 4 is right here, and you look at again that height. It's kind of like, that's how you find the value. If it's on the negative end, you just look at the height, but it's going to be a negative value. But in this case, we're talking about all positive values because it's above the x-axis. So T of 2, T of 4, you see T of 2 is above T of 4, then T of 2 is bigger. So T of 2 is larger in this case. And then it says for which values, x values find T, for which x values T of x is 25. So here's a nice way. You can draw the line at T of at 25. So this is like when the temperature is 25. Now you try to determine the corresponding x values for the intersection, which is here and there. So that's going to be 1 and 4. So we get 1 here and then 4 here, 2 of them. It says now find for which the temperature is greater or equal to 25. As you see, between 1 and 4, the graph goes above the 25 height. So that means it's above 25. If it's before 1 or after 4, it's going to be below 25. So it says we want here the temperature to be greater than 25. So in this case, this really happens between 1 and 4, and you need to use brackets because those are included because it says greater or equal to, equal sign is included. And then the last one, find the net change in temperature from 1 p.m. to 3 p.m. So this is like, I'm going from T of 3 minus T of 1. So it's the difference between T of 1 and T of 3 in order. So you look at T of 3 was 30, and then T of 1 was 25. So the difference is 5 degree Fahrenheit. That's the difference, net change in temperature from 1 to 3 p.m. You have to go in order. So for example, if it goes from 25 to 30, then when you subtract, you're going to get negative. That means here it increased between that time frame on average. That's really what it means. Like if you look at the change is positive. And you can clearly see that it was 25, and at 4 p.m. it's 30. So now we go to the next part, finding the domain and the range from a graph. So I hope this is recording, yes. Domain and the range from a graph. On the graph, the domain is the x values that the graph covers, and the range is the y values that the graph covers. Like in you see in this graph, you can just simply shade the graph covers on the y-axis and shade the part that the graph covers on the x-axis. It's like you're projecting it onto the x-axis and taking that interval. Look at this problem. So I'm gonna graph this using a graphing calculator. So this is similar to TI-8384. What you do is you go to y equal and then type it. So I go to second and then squared. That's going to be square root 4 minus, here's the variable x, and then I square that one. So then I click on graph. Then I see the graph. So it's a semicircle with centered at 0 and then origin 0, 0 and then radius 2. So we can just draw that one here. So it's basically what we really have is here. Here's 2, here's 2, here's 2. It's basically like graph looks like this. This is -2, this is +2, this is +2. So when you look at the domain, remember I said domain is the x values that the graph covers. On the x-axis, the graph starts at -2 and goes to +2. So that's going to be bracket -2 comma +2. On the y-axis though, if you look at the graph, it starts on the x-axis and it goes up to 2. That green part is the graph covers. It's kind of like if you kind of squeeze the graph onto the y-axis, that's the green one is what you're going to be getting. So that means the range of this graph is 0, 2. I use both bracket because those values are all included in there. So this was one example about domain and the range. Now let's look at this part. How do we solve equations or inequalities using graphically? So what you can do is, here we go. If a graph is above the other one, then it's bigger. So it's like its height is bigger on an interval. Like look at this first example in here. As you can see, G is bigger than F on the interval AB. But here, AB is included, so I'm going to make it greater or equal to. And on the bracket AB, because endpoints are included, because I include the equality. On this one, it's an open interval, so that means in this one, G is bigger than F. And I'm going to use the open interval AB, parentheses. And G is bigger in here because if you draw, like, think of that way, I draw a vertical line from one function to other. The one above is the G. As you can see, after B it changes, before A it changes, but you just check it interval by interval looking at the inception points. These are the points for which the two are equal. Like, let me show this on this example. So I'm going to graph them first. And then we will find in sections everything like graphically. So I first have 2x squared plus 3. Let's go in here and then write it. 2x squared plus 3. So this is the first graph. Let's take a look at the second one. It was 5x plus 6. So it's 5x plus 6. And then I graph them. So I need to change my window because y needs to be bigger. Let's change y max to maybe like 30, and then graph. Now we can see it. It's one is a parabola, the other one is a line. How can we find the intersection points? We're going to use second trace, and then we go to 5, which is the intersect. It says find the left bound, so I'm going to use the arrows to find the left bound for that. I hit enter and it says find the right bound. I find the right bound for it. You see, like, I'm kind of like capturing that intersection. Enter, and then I need to, let's see, then I need to make a guess, and then I hit enter. Oh, I'm sorry, it just already gave me the intersection. So in TI 8384, you may need to get a guess. There will be a blinking cursor, like a blinking dot. You have to move it close to the intersection and hit enter, and then it will give you the intersection. But here it's -0.5 and 3.5. Let me draw that. It's kind of like one is this parabola, and the other one is that line. This is just an illustration. This point is negative 0.5. So this is like negative 0.5 comma 3.5. I need the x point in there. So let's find the second one. So for the second one, we're going to do the same thing. Second trace, go to intersection, which is 5. And then now I'm going to move the left bound to the second, close to the second intersection point. Hit enter, and then choose the right bound. Enter. You may need to make a guess in here for TI-84, 83, as I said. But once you do this, then we got 321. So let's go in there. So this is actually 3 comma 21. So then this point is 3. So these are like x values. This is like x equals negative 0.5, x equals 3. So we got the solution to the first one. When they intersect, x needs to be negative 0.5 or x needs to be 3. So we already get that. In here, it says I want the parabola to be less than the line. As you see, between negative 0.5 and 3, line is bigger than the parabola. Outside, parabola is bigger. So in here, I want in the first one, I want line to be bigger. That happens between negative 0.5 and 3. I hope this is clear. You see, like I want parabola 2x squared. So this is 2x squared plus 3. And then this one is y equals 5x plus 6. So I want the line 5x plus 6 to be bigger. So in that case, that happens when you can just see, guys, here's the green one. This line is bigger than that blue one, which is the parabola. It's bigger. The green is bigger. So that's the case when you have B. So B happens, and it's like less nor equal sign is in there. So I have to include the endpoint. So this is going to be bracket negative 0.5 comma 3 bracket. That's how you have in between. Line is bigger. In the last one, you want the parabola to be bigger. Parabola is bigger on the outside. So it's kind of like up to negative 0.5 and up to 3. So that means the solution to part C will be negative infinity to negative 0.5, parentheses, because it's greater than, strictly greater than, equality is not included, union starts at 3 and goes to infinity. So that's what we have for this one. This is like how you solve the inequalities. Again, we're working with the graphs. How do you solve them? By using a graphing calculator. By using the graph. Right? So the next part, increasing, decreasing intervals. A function is increasing if it goes up from the left side to the right side, and it's decreasing if it goes down when you move from the left side to the right side. So like think of I'm walking on this one, on this graph from left to right. I'm going uphill, so it's increasing. If I'm going downhill, then it's decreasing. And then local maximum, local minimums are important points, turning points. That's kind of like, for example, let's say you have a revenue function and your revenue is going up, then it starts to go down. That means something happened in there to maybe investigate, to understand. So that point becomes an important point. That's like a turning point. And we call them local maximum, local minimum points, because if you see in the second graph, you take a small kind of interval around that point, your value becomes a maximum or becomes a minimum. So it's not maximum of the full graph, but it's maximum of that little piece. That's why we call them local maximum minimums. And there's an easy way to find them graphically, but I put this example over here. You can just check this first example, like local maximum, local minimum. Here's a local maximum point. Here's a local max. Here's a local min already written in there. Increasing intervals, you see it, and for increasing, decreasing intervals, please, we're using always the x values. Okay. and let me, so decreasing intervals, we use the x values. So for this one, it's increasing up to -2. So it's like negative infinity up to -2, it's increasing. Then starting from -2 to 2, it's going down, decreasing. -2 to 2. We use open parentheses because these are like what we call them in calculus critical points. So we just exclude them. And then after 2, it starts to go up again. So it's going to be 2 to infinity. That's how we write it. So, and the local maximum, local minimum, you can see that. It's already given in there. Now let's move into this example. This is going to be giving you. So as you see, we need to graph it, especially for the range. Domain is like, we can just clearly say domain is the all real numbers. No restrictions given in there. Let me fix that. No restrictions given in there. So it's like -infinity to infinity. You don't have any fractions to check or square roots to check. But a range, we need to graph it. So let's graph that 12x squared. So let's go here, clear. I'm sorry. Let's clear this one. So 12x squared, and then 4x to the third plus 4x to the third, and then minus 3x. Oh, move the arrow, minus 3x to the fourth, and then I graph this. Here's a graph. We need to make it a little bit bigger. We need to make it a little bit bigger, but you know, let's make the window size a bit bigger. Maybe like make this one 40, and graph this. So now we can just see that. So if you want to find that maximum minimum, again, you can use second trace, like second trace, and then go find the minimum. You just look for a left bound. See, there's like a minimum in there. Use that left bound, enter, and then use the right bound, and then enter. It's going to be 0, 0. And then you want to find, that point is really in there. But let's check the maximum. If you look at the left bound, and if you look at the right bound, you got 232. 232. So the graph looks like this. Let's illustrate that. So let me just check that again. The graph looks like passing through 0, 0. So this is just an illustration. So it kind of like looks like this. It's a 4th degree polynomial. So because just goes up like that. Here 0, 0 goes up again, goes down. So this point is like 2, 32. We know that this point is 0, 0. Here we go. Let's find the other local max. So second trace again, I go to find the maximum. So this is the way that you can try to solve the next problem. Go to left side, enter, and it's going to tell you -1, 5. It may just ask you to make a guess on a TI-83, 84. Just be careful with that. Just in the last part, take that guess close to the maximum and then hit enter. It's going to give you that maximum. So that's, what was that? -1, 5. That was -1, 5. So this point is -1, 5. So we just get this. So this is increasing up to -1. So the range, as you see now, range is not -infinity. The range, the graph goes up to the level 32. Can you see that? Above 32, there's no graph. So that means this range is -infinity, 32. Right? And then 32 is a bracket. And then we look at the increasing, decreasing intervals. So increasing intervals, decreasing intervals. So increasing intervals, it's increasing, so it's opening down. You see, the increasing interval is just up to -1. It's increasing. So negative infinity up to -1, it's increasing. Then -1 to 0, it's decreasing. -1 to 0, -1 to 0, it's decreasing. And then starting from 0 up to 2, it's again increasing. 0 to 2, it's increasing. Starting from 2 and infinity, it's going to be decreasing. So guys, be careful here. I'm using use x values, okay, because you're using the intervals from the domain for this. And then this function, we got local maximum value of 5 at -1, and then 32 at 2. As you can see, those are local max points. Like if you draw like a little piece here, that's going to be a maximum in there. Maybe if you draw a little piece here, that's going to be a maximum in there. Local maximum turning point. And there's a local minimum in here. So you can just see local minimum is 0 at x equals 0. I use the x values to locate the max min. I use the y values to actually give you the local maximum or minimum value. So I hope this video helps you to understand some concepts that we can get for a function from a graph, and hope you enjoy it. Thanks for watching. Bye.